Our next speaker is Libby Barnes from Colorado State University. I'll let you go ahead and do that. The fun factoid for Libby, I'm going to embarrass her a little bit.
Oh, no.
I
don't know the fun fact yet, so.
So she doesn't know I'm going to say it. But she just precisely 1 week ago, Libby was awarded the Meisinger Award of the American Meteorological Society. This is an extremely prestigious award for an early career scientist, so congratulations, Libby. Wow. And she's going to talk more about
You are embarrassing me. All right. Here we go. So you can't see anything, but it's coming. So I have the word atmospheric rivers in my talk, too. So Jim and I did coordinate a little bit, so I'm not going to tell you all the details of what these are. But really, actually, and I have precipitation, which is a word that gets a lot of people excited, but it's really a time scale that ultimately, hold on, can I make this actually a slideshow? Is that okay? Okay, let's see if I can break it. View, full screen mode. There we go. All right. But it's really a time scale I want to focus on today. So if you don't actually care about atmospheric rivers or precipitation, hopefully you'll still have something to take away from this talk, which is the approach. Okay, so first of all, I always like to embarrass my students and colleagues by putting photos up of them because I did not do this work all by myself. And some of my students will tell you I did very little of it. But they've been wonderful colleagues to think about these problems with. So let's think about forecasting or prediction. Here's a fun little schematic. Prediction skill, lower on the bottom, higher, so better on the top. And what's on the x-axis is how far into the future we're making a prediction. How far are we going? So, climate projections are way, way, way out here. So if we think about weather and weather events, if I tell you what the temperature is going to be tomorrow, maybe you'll sort of believe me, but that's going to go down as time goes on. And after about 2 weeks, we really aren't very good at doing that anymore. Okay? And that is known as, many of you may have heard, the butterfly effect, or this idea of chaos takes over, and small initial condition errors can really take over. So after about 2 weeks, it's really hard to make a weather prediction. On longer time scales, maybe beyond about 3 months, if you've heard of seasonal prediction, this is where we can really take advantage of things like the ocean. So El Nino, La Nina, those have memory in the system that allow us to say maybe in 6 months what something, say, precipitation might do over an area. But it's really, if you notice, there's a gap. Okay, and this is sometimes called the sub-seasonal to seasonal prediction gap, or S2S, because we love our acronyms. Okay, and the idea is, we can do weather pretty well here, and that's what the timescale Jim just talked about. And we have seasonal outlooks out here, but what about this middle time? And we actually did hear today already, it came up a few times, that this time scale is actually really important. And I'll talk briefly about that soon. So this is my cute little schematic. We have to bridge the gap, right? Okay, how are we going to do that? Today I want to talk to you about some ways to think about bridging that gap. And I'm going to talk about 2 specific phenomena we're going to use. That is not to say it's the only way to do it. It's the way my group has been thinking about this problem and the types of problems we're doing. And that is, we're going to do more alphabet soup here, which I will define, using 2 climate phenomena, the Madden-Julian oscillation, which we already heard from Jim, the MJO, and the quasi-biennial oscillation, or the QBO. All right, and we'll get there. But these are 2 tools or climate phenomena we're trying to use to bridge this S2S prediction gap. Okay, so why might we care about this gap? Maybe we're fine without it. Who needs to know what's going to happen in 4 weeks? Well, most of you are probably laughing, going, that'd be really nice, actually. But let's think about weather timescales. Okay, why do we care about weather forecasts being any good in a week's time? With things like hurricane evacuation, thinking about severe outlooks, weather outlooks. On seasonal timescales, sometimes we think about Arctic shipping routes. Trading is often done on these longer timescales. But it's at these S2S timescales that people are making decisions about where their ships should go. They're trying to get emergency equipment to the general area. Something may happen, so when they know exactly that city or that location, they can go and act. And we already saw this is the Oroville Dam spillway. Reservoir operators wanted to know if we, on about a 4-week timescale, are we going to get more rain? If we are, we should let water out. If in 4 weeks' time we're not going to get more rain, then we should hold on to it because we need that water for the dry season. So especially, I would say California has shown a lot of interest in research on this S2S timescale for these reasons. Also planting and crops, decisions are being made on these 2-week to 2-month timescales about whether I should plant my crops, do we have another frost coming, et cetera. Okay, so where should we look to bridge this gap? I already told you this butterfly effect is real, and it's chaos of the system is a problem. But it turns out there are different directions we can look, and someone years ago posed it this way, and I really liked it. So we can look up, we can look down, we can look north, and we can look south. We need information from somewhere to tell us what's going to happen. So we can look up into the stratosphere, down to the Earth's surface, north to the Arctic, or south to the tropics. And today I want to tell you about looking up. Well, it's sort of up and north, but it didn't go as well as my schematic here. And then south to the tropics. Okay. So we already saw cool pictures of atmospheric rivers. Here's a few reasons why you might still care if you don't already. This talk is mostly going to show you plots of the West Coast. I am aware we're not on the West Coast. I will show you some more US-based plots, but as I said, or figures, if you get nothing out of this, because everybody's tired, you all want to have a nice reception, it's more the time scale and the thinking rather than the specifics of California versus Florida. Okay, so just pointing out, too, it's not just California. It's also Alaska. A huge landslide happened on January 24th, 2014 from a wet rain atmospheric river coming and hitting and blocking this roadway, so a town was unable to get any cars in or out for over 3 days. So these things are important there. And the Midwest, the summer flooding of '93 has been largely attributed to atmospheric rivers pummeling the central US. So it's not just a California problem. Okay, so can we forecast atmospheric rivers on these timescales? That would be nice. So we took, you can take an operational model and try to forecast individual atmospheric events on a variety of timescales. So 2 days out, 3 days out, 4 days out, 5 days out, all the way to 14. So here's our 2 weeks. Here's my cute little butterfly. And not surprisingly, no matter where you look, that skill, this is how well you do, drops off drastically by the time you get to 2 weeks. So these are with our weather models, okay? And so the idea is, hey, this butterfly effect is a real problem. We know about it, so maybe we're all doomed. And of course, if we were, then I would be done. So the idea is, how do we use these climate phenomena to bridge this gap, since we can't just run our weather models a few more days? It just won't work, okay? And so I'm calling these empirical models because we can't use our weather forecast models to do this, or we can't yet. I have high hopes. But we're going to go backwards and actually do really simple models. And by empirical, I mean really statistical. But there's not a lot of stats, don't worry. I'm going to maybe add some things up. Okay, and that's about it. So can we make forecasts based on data analysis of the observed record, of what's happened, learn from what's happened, and use that to make skillful forecasts? So this idea that we can look to the tropics for sources of predictability. Okay, that's first the important part. And the second important part is what I have in italics. I am not going to be able to forecast. So, if your birthday is in 5 weeks and you want to know whether to get a tent or not for your outdoor party, I'm not going to be able to tell you, at noon an atmospheric river is going to come, or heavy precipitation. But maybe what I can do is say, hey, over that week, you might expect more rain than normal. Or when we get really good, maybe you can start setting thresholds of percentiles. What's the probability I'm going to get more than my typical extreme, 75th percentile event or something? Okay, so that's what we are forecasting, not individual events. All right, so what is this MJ or Madden-Julian oscillation? Here's my cute little schematic. So we've got storms and precipitation down here in the tropics, tropical convection. And it creates a wave. The H is a high and the L is a low. And there it goes. It propagates, sort of. All right. And ultimately can then impact where storms are steered along the West Coast. Now, different phenomena occur if you are interested, say, again, in the eastern US. But the idea is generally the same. That we have these tropical to mid-latitude or tropical to extratropical interactions through these waves. I like to think of the MJO as a big hammer. Okay, and the atmosphere is sort of like, well, let's say a rock. And the atmosphere is sort of like a lake. And it's throwing a rock into that lake. It's sending out ripples. And these ripples are now influencing where it rains. at higher latitudes. There we go. All right, and here's a much prettier picture of the Madden-Julian oscillation. We split it into 8 phases. Jim briefly mentioned this, but these phases tell us where we have clouds and rain. So if you're in phase 2 or 3, you have clouds here in the Indian Ocean. And if you're in phase 7 and 8, you're over here in the Western Pacific. So it helps us tell where those storms are. Okay? And we're going to use this because depending on whether my rock has been dropped in the Indian Ocean or whether my rock is being dropped in the Western Pacific, it's going to send different waves out, which will then impact precipitation and storms over the United States in different ways. Now, the really neat thing that's sort of special about this phenomenon is how fast it propagates, how fast it moves from the west to the east. Turns out it moves about, and this is all, abouts. We can find lots of things that don't agree with this, but on average, each phase lasts about 5 days. So it's about 5 days to move between this position, this position, this position, and this position. What that tells us, though, is that if we know where it is today, and it's in phase 1 or 2, we can start to guess where it's going to be in the coming weeks. And on top of that, it takes time for this wave to propagate from the tropics to the US. So that's additional time we have to start to figure out what the impacts will be. Now here's the second of the alphabet soup. This is, I just told you 2 here. And this is the quasi-biennial oscillation. And this is a second source of predictability. So looking up into the stratosphere. I told you we'd look up in north. We're actually looking up in south, sorry. And this phenomena is far above, where we live. It's up in the stratosphere up here, right above where, in essence, planes fly. And it tells you which way the wind is going along the tropic or along the equator. So we have eastward motion or we have westward motion. And the thing is, this happens, it switches signs about every 2 to 3 years. So if you know what it is today, you probably know what it's going to be in about 3 weeks, right? So that's a good thing, because that's really helpful. Also, there's been a lot of work by, in addition, people in this room, looking at how this climate phenomena impacts clouds and storms in the tropics, which is where our Madden-Julian oscillation lives. So these 2 things can interact with each other to change our ability to understand these waves and potentially predict whether it's going to rain or not in 3 weeks' time. So we're going to look at the interplay of these 2. And is it useful? Oh, here we go. OK. So this is the one kind of plot I'm going to be showing over and over again, because this is how we've thought about it. What I'm going to show you is where the storms are in the MJO on the y-axis and how far into the future we're looking on the x-axis. OK? So you can think of it as sort of today, where are the storms? And then you want to look out 3 weeks' time and ask, if I'm sitting in Seattle, do I expect more atmospheric river activity or less? If it's red, it means you should expect more. If it's blue, it means you should expect less. Okay? And these plots are pretty. You see these stripes here? These stripes are showing that this convection is propagating in time. That we have information today, it tells us about what's going to happen into the future in a very systematic way. Okay? So we can actually use this, say, to ask, if it's the convection is sitting over the maritime continent, in 3 weeks, we should expect fewer atmospheric rivers hitting Seattle. Now, if this is California, we could say something like to the reservoir managers, we might expect less rain in the coming weeks. This is, though, when the QBO, that stratospheric phenomena, is the winds are from the west. When the winds are from the east, we also get stripes. But do you notice how if today is phase 5, so the storms are over the Indian Ocean, and we go out 3 weeks, we get the opposite answer, right? We get more atmospheric river activity. So the point being here, if you didn't split by what the stratosphere was doing, you'd think there was nothing there. You wouldn't realize that there was actually something systematic going on. And we can look here and see, these are legitimately cherry-picked examples of what's happened when we were in an MJO phase 5, and 3 weeks later, indeed, we did see atmospheric rivers hitting the Pacific Northwest, and then also in QBO West, the atmospheric river being diverted to Alaska. And we understand why this is, but I'm not going to go into detail here. The point is this information is useful for figuring out what's going to happen in 3 weeks' time. OK. So then the real question is, these are just pretty averages, but I haven't actually done a real prediction where I assess my skill. Was I actually able to make a skillful forecast that could be useful? And so what we're going to do is something incredibly easy. We are going to look at these plots. This is the fancy way of looking at it, taking the distribution and shifting it based on what's going on in the stratosphere and the MJO. But really what I'm going to do, what this fancy plot is just showing, is this figure here, and it's using this as a table. I'm just saying, hey, if today is MJO phase 5, every time it's 3 weeks from now, if the QBOs is from the east, I'm just going to make that prediction. It's that simple. I'm not using a fancy model. So statistical here is meant in quotes. It's pretty simple, just using this picture. Okay, so it's shifting. The question is using the shift of the distribution here. And we can do that, and this is what we get out. Now we see these stripy plots again, but the important part is these are now a quantification of skill. How good were we? We actually went through the observational record, made predictions, and said, did we predict it right? How'd we do? And the answer is we actually do have skill, and we have skill out. If you want to do statistical significance, you can look at the little dots of varying colors for different sizes. We can get out into 30 days or so ahead of time, depending on what is happening in the tropics. Okay? Do you notice the white? The white says, I have no idea what's going to happen there. I have no skill. Well, we can always make a forecast, whether it's any good or not, right? The white tells us, you know, this method did not work well. Okay, so if you happen to have your birthday party and today is MJO phase 4, so again, the storms are sort of over the maritime continent, and your birthday is in about 18 days, I'm sorry. I don't know what to tell you. And this is a different philosophy than the typical sort of weather prediction, which is we will always have a prediction for you. You know, you don't pull out your phone typically and it says, I decay. You know, I don't know what the temperature is going to be tomorrow. And this is a very different philosophy from that. So again, the cool thing is, again, we also see these stripes. From the dynamics perspective, from the physics and science perspective, the stripes tell us we think we're getting skill for the right reason. We think we understand the phenomena. It's not a scattershot of random blobs all over the plot. And we can go to the state-of-the-art weather models and ask, hey, if we try to assess them similarly to our simple metric, how do they do? And again, they really lose skill down to 0 by about that 2-week mark. So the point is we are going beyond what our weather models can do, potentially by 2 to 3 weeks. Okay, this was, by the way, for British Columbia. It works for California, in some places not as well, but especially here under easterly QBO. And again, for California, ECMWF, one of the best weather models, also cannot do this. So there's skill here from these phenomena, and we think we understand where they're coming from. So we can also look, now you might say, Libby, I don't actually care about atmospheric rivers, okay? Which would make Jim and me sad, but okay. But you might care about precipitation, and Jim showed that atmospheric rivers bring a lot of precipitation. So what happens if we forget about atmospheric rivers, these plumes, filamentary features, and we just forecast precipitation? Was it really wet or really dry? Was it anomalously high or low precip? And again, these methods show us these stripes, and the stripes tell us we think this is due to the MJO acting like a rock, if you will, again on our atmosphere and sending these waves to the US to impact where the storms go. So we also have skill in California rainfall. And note, in this particular case, if we totally ignored what the stratosphere was doing, it wouldn't look nearly as impressive. The darker colors mean we did better. And it's because we had to separate them out because they sort of canceled each other. So the idea here is we have to care about more than just one thing, more than just one climate phenomenon. Okay, so this leads me to the second concept, or the concept I really want to get home here, is this idea of forecasts of opportunity. This idea that there are windows of opportunity when we can make a skillful forecast at these timescales. But at least currently, I cannot make a skillful forecast at all times. So it is possible you'll come and say, Libby, I really need to know what the rain's going to do in 3 weeks. And I might have to say, I'm sorry, I have no way to know that. Past data doesn't tell me, isn't consistent. On the other hand, you may come and ask, and I might say, oh, actually, we have skill then. Okay? And this, again, is a very different concept than the typical make a forecast all the time. But I think it's still useful because it's better than nothing, which is currently sometimes how it feels at 2 weeks to 2 months. So a student of mine, Kyle Nardi, went through and started, here we go, Florida's in here now, started saying, okay, how often do I have these forecasts of opportunity that are skillful, that actually have skill, not just I make a prediction and it's terrible, but I make a forecast or a prediction and it's pretty good. Okay? And this shows, we've done this for all seasons of the year. This is for spring precipitation, so March, April, May, all over the entire US. And the darker colors mean there are more opportunities where if you came to me and asked, can you make me a prediction, I would say yes, and I have skill associated with that prediction. So it's not everywhere. You have to sort of get lucky that you care about one of the regions that is dark green. But if you do, there is information there. And this is, again, looking out 15 to 42 days. So we've aggregated a lot of weeks. We can also ask how important was that stratospheric information compared to just the tropical information? Remember I tried to argue that you need both of them in this case? This is showing you how much more important, or how important the stratosphere was in making those opportunities. And the point is, it's pretty high, especially over the West Coast, saying you need to care about more than one of these climate phenomena. You need to actually understand both processes to get this forecast. Okay, and this is a paper that's currently under review, if you're interested. We have done a lot with this toy, or simple, it's not a toy, but simple statistical model. We have looked at things like hail and tornado activity in spring and showed we actually do have skill out to 4 to 5 weeks for weekly activity of both of these severe weather events. Precipitation, atmospheric rivers. And if you are wondering about your favorite location, I clearly didn't have enough to do one day last summer, and I made a web app where you can go and we have all of our data that's gone into all seasons of the year, all combinations, all phases of QBO and SO. And then you can look at precipitation, temperature, integrated water vapor transport, and atmospheric rivers, and look over different averaging windows and see where you could have skill with such a simple model, if you're curious. And you can make the little plot. This took me way too long to do, so please try it. Make it worth it. And you can make plots, too, of how often you had opportunities. How often were you actually able to make a skillful forecast? All right. So to finish here, how many minutes do I have? 10. Okay. So we've shown there's information in the real observations that we can extract to potentially make predictions beyond what our weather models can do. That's super exciting because the real world data, we do have that. Okay? That's great. The question now is, can we do better? If this information is sitting in there, and the simplest thing we could think to do was just look at how, what happened in the past on average and use that as our model, and it did okay, maybe we can do better with more sophisticated tools. So something that I'm doing a lot with all of my work is machine learning methods, and I don't mean to bore you with ML over and over again. I really see it here as nonlinear regression. So far I've been doing averages, and now I'm going to make it a little bit more nonlinear. But it seems to me that these methods are perfect for data mining the observations because we now know something is there. We've done it without these methods. Now let's see if we can go in and get it a little bit better. Maybe we can improve upon what we've already done. And these are really preliminary, and I guess the point, again, is not going to be the actual numbers, but this is the way we're thinking. And I'm optimistic good stuff will come out. So, bet you didn't think you were going to see one of these today. All right. If you're not familiar with a neural network, but you're familiar with a line, then you can figure it out. The idea is you have two inputs, a value and a value. You multiply them by a weight, and you add them up. That's what we have here. And then you add a y-intercept, if you will. Okay? And then we stick it through something super nonlinear and make it really complicated. But otherwise, it's just linear regression with this function that makes it nonlinear. This is not important for actually understanding what we did. I just always like a reason to show people what a neural network is. Now, this may look simple, but now we can string them all together, do lots of lines, lots of linear problems, stick it through nonlinear functions, add those up, do it again, again, and again, and as you can imagine, they get really, really complicated really fast. And the neat thing, and this is a movie that won't work, but ultimately, we can all fit a line here. We learned in middle school or whatever, at least our calculators drew the line for us. We can use a neural network, this is actually a neural network, in fitting a line through this data iteratively, so it ultimately can figure out where that line is. That's what we're doing, but now we're going to do it in multidimensional space, so it gets complicated. So we've seen this plot before, just different color bar, where I'm looking at how well this simple statistical model did. This is the one I already showed you. And I always tell my students, don't go and use something fancy if you haven't checked how it did to the simpler version you already did. So that's our first step. We have a really simple network that takes in information about the MJO and tries to predict whether atmospheric rivers are going to hit that region or not. And this is what we get out. And it looks sort of the same, actually. You notice that? I mean, I'm not trying to sell you here. I'm trying to sell you on the idea. So that's good. We didn't do worse, which is definitely possible. But we have skill. OK, great. But now we can start to play other games. I'm going to skip that. We can start to play other games where we say, now I'm going to input, instead of just what the MJO is doing, I'm going to input a map of the tropics today. This is what the tropics look like. For those of you familiar, this is outgoing long-wave radiation. I'm going to input that map, and I'm going to say, hey, neural network, are we going to get an atmospheric river in 18 days over, where am I looking here? British Columbia. And it can take this information and tell me what's going to happen. OK? Yeah, great. And it does well. But this is what's cool about this method compared to our simple model. As scientists, we say, oh, but I don't know what's happening inside. It's a black box. This is really complicated. Who knows what's happening? There are tools to tell us what part of the tropics were important to make this prediction. And now we can start learning about the physics and the dynamics of this problem. And so we can use visualization tools. The idea of, you take your backpack, you put it through an X-ray machine, and you get an inside view. It's not a perfect inside view of what's going on, but it's better than nothing. We can use these tools, and I'm going to skip this, here, focus here on the cat. For example, we could input an image of a cat and say, hey, neural network, where did you look to know that there was a cat in this image? Guess where I looked? Where there's a cat. Not surprising anyone, right? See how it's red here? It means the neural network looks there. But that's actually pretty cool. It knew to focus on that part of the image. Now you might say, this is a cat. But remember, I'm inputting physical variables into this neural network and having it make a prediction about something weeks in advance. It would be pretty cool to know what information it was using to do that. And so I can do that, which regions of the tropics were relevant for correctly predicting atmospheric rivers on these subseasonal to seasonal timescales. And I can make maps like this, where the darker red colors are telling me the regions that were important, where the neural network looked to make its accurate prediction. And this is where I get a little technical, but interestingly, especially these regions here, are well-known regions of where the Rossby wave source is located, or where the rock does its best job of making waves. So it's looking in the right spots, and we can start to go back and learn some physics. OK, so in wrapping up here, what I'm most excited about for these problems is that we have a limited observational record, only about 40 years of satellite data to test these ideas, because our weather models can't quite do it yet. We've seen Jim talk about the fact that our climate models also have some problems. But we do have a lot of climate model output. It may not be perfect, but we've got a lot of it. And there are neat tools out there in the computer science community that say, let's learn from imperfect data, but that's sort of like reality, or sort of like the problem we're interested in. Let's refine it with observations and ultimately output a model or a prediction model that's even better than either of those combined. And if you're interested in these topics, come find me later. OK, so summary thoughts. These forecasts of opportunity are key to the success, in my mind, of S2S prediction of extreme weather. We're not going to be able to make predictions all the time for everybody. But if the timing is right, we may have a good amount of skill. And we can tell you when those times are. And that we can actually skillfully predict ARs, precipitation, tornadoes, and hail up to 4+ weeks in advance. So the big question is, how are these two different climate phenomena interacting? And I want to finally end here with more advanced methods can help us identify these forecasts of opportunity and can be really used with prediction and understanding together. And finally, I just want to wrap up here and say, I haven't talked about climate change at all yet. All of these, these phenomena, the Madden-Julian oscillation, what's going on in the tropics, are impacted by what's going to happen as the climate warms. So one of the big questions is, are the tools we're learning that work today going to work in 20, 30, 40 years? And one of the somewhat depressing things my colleague Eric Maloney has been looking into is that that rock, if you will, that the MJO is on that lake, is getting smaller as the climate warms. In essence, it makes smaller ripples. So it has a harder time impacting what's going on over the US in the weeks to come. What does this mean? It means that we may have a lot of skill now, but could it go away as we go into a future climate? And that's, I think, where the state of the art is for some of this work. So thank you.